recording. Okay, today we're going to be talking about chapter 16, the fundamental homomorphism theorem. Um, so we're going to make a relationship between homomorphic images and the quotient group that we've seen in the previous chapter. And it starts off by theorem 1. Let f be a function from G to H, be an homomorphism with kernel K. So kernel, I read a couple chapters before. We read, and I just reminded myself. So kernel is the set of is a subset of elements out of which, when you apply f, you go to the neutral element, right?
Yep.
Yeah. Then f of a equals f of b if and only if ka equals kb. In other words, any two elements a and b in G have the same image under f if and only if they are in the same coset of k. Okay, my first question is, why do we need the coset stuff? Because, yeah, that's my first question. What does it mean to be a coset with kernel? I guess that's my question.
Uh, well, you know what a coset is, right? You still
Yeah,
remember that.
yeah.
A kernel is a subset of G. Actually, it's technically it should be a subgroup. I'm pretty sure. Um, but anyways, it is. It is the basis on which you can partition G in such a way that. Oh, this is actually something that we'll see develops throughout the chapter, but Uh, you basically need this in order to actually relate like the homomorphism with the quotient group, because remember a quotient group is defined in terms of you have a subgroup which it must be normal, and then you use that to partition the original group um, into subsets which like they don't overlap and altogether they recover the original set, right?
Mm-hmm.
Um, and there were a bunch of theorems we saw about relating like elements to the cosets of this that form this partition.
Okay. I think it's better for us to just go to this image because my question is kind of in here anyway. So in other words, yeah. So the proof for this theorem is kind of like trivial if you think about it, because we start by f of a equals f of b if and only if, but if they are the same, we can do this is also true, right? Um, because you're just if they are the same, if you grab one with its own inverse, is equal to neutral element. But then this, because it's a normomorphism, this is true, right? So f of a, f inverse of f of b is equal to f of b inverse. And we know because this is true, AB inverse is in K because of the definition of kernel. Then using the previous theorems from before, we have Ka equals Kb. So what this theorem really tells us, it says that if F is an homomorphism from G to H with kernel K, then all the elements in any fixed coset of K have the same image. And conversely, elements which have the same image are in the same coset of K. Um, yeah, so my question is kind of like in this image really. Because if you are like, okay, how should I say this? Hmm. I think I understood my question, because my question from before was, if you are in relation to kernel, if you go to F, why isn't everybody converging to neutral? But it seems to me that the answer to that question is you are in relation to kernel, but you are in a coset with kernel, which means that you have something that is outside of K, which is A and B here. And that is why not everybody is converging to E.
Yeah, remember a coset is actually different from the original set you used to build
Mm-hmm.
the
Mm-hmm.
coset, right?
Yeah, it is therefore clear already that there is a 1-1 correspondence one-to-one correspondence matching cosets of K with elements in H. It remains only to show that this correspondence is an isomorphism. But first, how exactly these correspondence match up specific cosets of K with specific elements of H? Clearly, for each AX, the coset KX is um, um, is matched with the element f of x. Once this is understood, the next theorem is easy. For each x, the coset kx is matched with the element f of x. Interesting. Theorem 2. Let f be an homomorphism of G onto H if K is the kernel of f, then and then K is the kernel of f. Is that a nomenclature we used before? I thought K kernel was related to groups.
F is an homomorphism, so kernel is related to homomorphisms, and F is one, so K is the elements that F maps to identity, essentially.
Um,
I'm not sure if that was the confusion.
no. But let me see if I find. I have the book here on hands. There is a definition of kernel, and maybe I am confused, but I thought kernel stuff was not related to functions really. Oh, okay, no, it is related to homomorphisms. My bad. It is related. F, the kernel of F is the set K of all elements of G. So, okay, so it's related to these G elements here. My bad. Okay, so the the proof now to show that, well, if K is the kernel of F, then we say that H is isomorphic to the quotient group G by K. Right? To show that G by K is isomorphic to H, we must look for an isomorphism from G by K to H. We have just seen that there is a function from G by K to H which matches each coset Kx with the element f of x. Call this function, what is this?
It's phi, I think.
Phi, yes. Thus phi is defined by the identity, so this is going to be the phi. This definition does not make it obvious that phi kx is uniquely defined. We must make sure that if ka is the same coset as kb, then phi ki is the same as phi kb, that is this thing. But this is what we just proved in the previous theorem, right? So if and only if this is true, then this is also true. Now we need to show that phi is an isomorphism, so it's injective, it's surjective. And then theorem 2 is called the fundamental homomorphism theorem. It asserts that every homomorphic image of G is isomorphic to a conjugate group of G. But I guess that kind of makes sense, right? Intuitively, when you have an homomorphic image, you have put a focus lens on the group, and that focus lens is isomorphic to the quotient group that come out of the interpretation of doing a factorization, right? Because the quotient group, as we've seen before, it's essentially factorization. So this kind of makes sense to me. Like, it's important to have the theorem and stuff, but to me this relationship is very expected, very much expected. Which specific quotient group of G? Well, if F is a homomorphism from G onto H, then H is isomorphic to the quotient group of G by the kernel of F. The fact that F is an homomorphism from G onto H may be symbolized by this writing, and then we can put the K down here to indicate that the kernel, that it's G by K, right? So the fact that K is a kernel, blah blah blah, does in capsule form. The fundamental homomorphism theorem says that if this is true, then this is true. Then we have an example. So we have here the function that we've seen in chapter 14, which was the introduction of homomorphisms, which is an homomorphism from modulo 6 to modulo 3. Visibly, the kernel of f is this. Why is that? Because if f goes to 0 goes to 0 and 3 goes to 0, and 0 is a neutral element in this case, so that's kernel of f, which is the subgroup of modulo 6 generated by multiples of 3. That is the subgroup 3. The situation may be symbolized by this writing. So if you want to go to from modulo 6 via the kernel of this f, which in this case is multiples of 3, you go to multiples modulo 3 actually. And then we conclude that the modulo 3 is isomorphic to modulo 6 by kernel of f, which in this case is multiples of 3. For another kind of example, let G and H be any groups and consider the direct product. So you have pairs in which the first members of the pair ranges over G and the second member ranges over H. You multiply ordered pairs by multiplying corresponding components. So this is what makes it an homomorphism. Now let f be the function given by this thing. So this is second, the function second. It is to check that f is an homomorphism. Furthermore, this is the kernel in which if and only if f grabbing the second is equal to e, that means that the kernel of f consists of all the ordered pairs whose second component is e. Call this kernel G star, then this is the definition, right? So pretty simple. We symbolize all this by writing. So this, right? So you start from the pairs. I use G star as the kernel. You go with the homomorphism to H. By the fundamental homomorphism theorem, we deduce that H is isomorphic to GH by G star. It is easy to see that G star is an isomorphic image of G. Thus, identifying G star with G, we have shown that, roughly speaking, GH by G is isomorphic to H. So what have we learned here? What the fundamental theorem of homomorphism teaches us? It teaches us that you can write, you can always write an homomorphic image as a quotient group by using the kernel stuff.
Well, it's a bit deeper than that, right? It actually establishes an isomorphism between those two things, so in some sense they are actually the same.
That's why I said they can be written as because they are one and the same. So every time you see modulo 3, you can replace it with this, assuming you can do the mapping with the isomorphism. But my understanding that this is always going to be true, though. Like you can always going to be able to create the isomorphism. If you have an homomorphic image, there will be a way to represent it as a quotient group and vice versa. Pretty cool. Pretty cool. So let's go over the exercises. You have 47 minutes. So A, does anybody have questions about A? Well, not questions, comments, like highlights.
Not really, I guess, other than, well, there are some very loose ties to number theory because a lot of examples are the modular groups, right?
Yeah, modular arithmetic. And then it comes B. Like, are these high order functions? Like, the first time I read this, I was like, wait a moment. This fancy F that I don't know how to pronounce. This thing takes, like, there's an alpha that takes an F, and it's the same as calling F applied with argument 1. So this is alpha is a high order function.
Yeah, it is.
And beta is also a high order function.
Also, yes.
So these two things, alpha and beta, they are essentially pinning down the things, that go over 1 and 2. Is that fair? What I'm saying?
Uh, yeah,
That
they're
is,
basically
yeah.
saying, okay, if you give me a function, alpha is saying, okay, if you give me a function, I'll give you the result of applying that function to 1, no matter what the function is, right?
Tev?
No, I was just going to say what Marinho just said in different words.
Yeah. So let J be be the set of all the functions from R to R whose graph passes to the point 1, 0. So this is assuming that there's a line, right? Marinho said it could be anything, which is true, but this be true thing is assuming that that's going to be a line. And let K be the set of all the functions the graph passes through to 0. So J is going to be the set of all the possible functions that when applied to alpha, that can be applied to alpha. And K is going to be the set of all the functions that will do what beta does. Use the fundamental homomorphism theorem to prove that there is an isomorphism between the higher order function in respect to J and the one with the K. But this is very like intuitive, right? Like we don't need to do the mechanical portions of this exercise to understand what this is going to. I think this is pretty okay. And then the conclusion
Uh,
is that that they are even isomorphic among each other, because there is of course a one-to-one correspondence between all the functions, between all the graphs that passes through the point 1, 0, and all the graphs that passes through 2, 0. Yes, Marinho.
yeah, basically it's giving you the two homomorphisms and the kernels, right? Because if a function passes through the point 1, 0, that means if you apply f if you apply that function to 1, you get 0. So like that means that this is the 0 will be the final output of alpha of that function, which means that function goes to identity. So that's part of the kernel of the homomorphism, basically.
Yeah. Comments about C?
Uh, Not really.
Yeah. Yeah, that sounds pretty fine, actually. Uh, so the homomorphism is essentially like doing the squares, right?
Yeah.
That's pretty okay. Um, D, inner automorphism. So there is a little bit of a definition going on. So let G be a group, be an automorphism of G, we mean an isomorphism. So you to yourself. This is the symbol used to designate that. Prove that the set alt G with the operation composition is a group by proving that alt G is a subgroup of SG. What is SG?
That's the symmetric group over G. That is, it's the group of all the symmetries of G.
Are these the permutation things? No.
Yeah.
Oh yeah, there it is. Okay. Okay, this is pretty straightforward, right? Um, if you use composition as operation, you're gonna be able to prove that that's gonna be a subgroup anyway.
Intuitively, you can think that the automorphisms of G are all of the permutations of G that happen to preserve the algebraic properties of the operator.
Yep, pretty much. Um, and then by an inner automorphism of G, we mean a function phi a of the following. For every x in G, um, phi a of x conjugate stuff. Prove that every inner automorphism of G is an automorphism of G. I mean, okay, how would you guys go about this one?
Hmm.
You essentially need to prove that all of the elements are in G. All of these elements, like all the possible, are the conjugates in G. If you prove that, I think you prove this.
Hmm. Well, do you have to prove that? Because G is a group, and you're taking an element of G and applying the group operation to another element of G, and you're doing that twice. So,
Yeah, but we don't know if A is in G, right? We know that X is in G, of course, but what about the A?
how can you possibly apply the group operation of the group to something that's not in the group?
Well, I don't know, because here's the thing. If you just assume that A is in G, this becomes trivial, right? Because here's the thing. You know that this is the definition of an inner automorphism. The definition of an automorphism is just you have to prove that whatever this does, you keep yourself under G, because then this holds, right? That's my understanding.
Yeah,
So if this is in G, then you are fine, because then you are going from X, which is in G, to something else which is also in G. Then this is true, and then we are good. So you're saying that this is like obvious then, like trivial because A is in G. What's your thought process?
uh, well, I don't really see how you could pick an A that's not in G, and then if you know that A is in G, then like you're just applying the group operations, and G is a group, so the operation is closed over that group.
We could pick an A from a well, G could be a subgroup of a larger group, and A could be in the larger group and not in G.
Mm. Okay, that's true.
Hmm. Hmm.
So there you go. And there's another thing. If we prove that this is somehow abelian, then we are also fine, right? Because then this is just identity, which is definitely an automorphism. If you can manipulate this thing. But I don't know if we can prove that this is abelian.
If we prove that um wait, the elements are phi A X. Um,
Yeah, I that's why like I think this is not that easy actually. Like there is some
the
sort of
operation
catch.
is composition.
Yeah, let's move on. If anybody has any tips on this, we can deal with this later. If anybody has like an epiphany or something. Any other comments on what are we D? Yeah, on D.
Hmm.
Hadn't you?
Uh, Not really, I guess. Like there's a connection to centers, but
Mm-hmm. Yeah. And yeah, the center being the elements that actually do, you can do the stuff, the commutativity operation property thing. And then we have E, the theorem applied to direct products and groups. Let G and H be groups. Suppose that J is a normal subgroup of G and K is a normal subgroup of H. Show that this function is an homomorphism from G, H onto a pair of quotient groups. That's pretty crazy, huh? No, but I guess that makes sense, right? Because we are using J to construct the quotient group for the left side and K as for the quotient group of the right side, and those are becoming pairs after F, so that becomes the answer for that.
yeah, actually you're constructing cosets, but yeah, the cosets are part of this quotient group.
Yeah, you're gonna use those as the cosets for this quotient group. That's what I meant. Find the kernel of F. Use the theorem to conclude that they are. Oh, actually, this is something different. So you have the pairs, quotient group with some other pairs. That's isomorphic as doing like G with J and H with K. Pretty cool.
Yeah, this is analogous to how multiplication of fractions works.
Yeah, at the end of the day, everything is just about doing arithmetic with things that are not numbers.
Well, rational numbers for the win, I guess.
No, in this case, right? But we did some math, we did some arithmetic with other things last chapter as well. First, isomorphism theorem. Now, any other comments about E? I should say.
Mm, not really.
Okay. So F, first isomorphism theorem. Let G be a group, let H and K be subgroups of G, with H a normal subgroup of G. Yes? Prove the following. So H intersection with K is a normal subgroup of K. Um, Interesting. So you know,
This
yes, Devo.
oh, this is true because H intersection of K is a normal subgroup of K. Sorry, I'm a bit slow today, but
Yeah, no, but that was funny. This is true because this is true. That was funny.
uh, no, I worked this out before, but I forgot.
Yeah, because here's the
Well,
thing. H is a subgroup of G, and K is also one of those. And we only know that H is normal, but it's normal in respect to G. So how can we say that intersection is normal in respect to K?
well, intuitively,
Because
because we know H is normal, and we know that H, K, and G they all have the same algebraic structure because H, K are subgroups or G, so they use the same operator, right?
Yes?
That means any elements that K has that it shares with H will also share the property, the same structure. Like they're working with the same operator, right? So they will have the same algebraic structure, which means if you intersect those two sets, you're basically making sure that any elements from K that would prevent it from being a normal subgroup will be eliminated.
Yeah, no, but to me, the intuition says that this is the normal subgroup of G. But we have to prove that it's a normal subgroup of K.
Well, it's because that's an intersection, right? Whatever is in the intersection will belong to both sets.
Mm, Well, I guess you could also say that H intersection with K is a normal subgroup of H as well and G. Like, this is a normal subgroup of everybody.
Yeah.
Okay, that's fair. If HK, so the like combination of elements from H and K, then HK is a subgroup of G. To me that's very intuitive as well, right? So we know that H is a subgroup of G, a K is a subgroup of G. How can their combination not be a subgroup of G, right? Makes
Yeah.
sense. H is a normal subgroup of HK. Well, yes, right? Because H is a normal subgroup of G, and HK is a subgroup of G as well, so H must be a normal subgroup of HK as well.
Yeah. Actually, for point 3, I think the salient thing to pay attention to is all of H is inside of HK because HK is the combination of elements from both of them, and if you combine every element of H with the identity from K, then you
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 got
know
H.
that every element from H will be there.
Yeah, that's for sure. Every member of the quotient group HK by H may be written in the form HK for some K in capital A. So every member of the quotient group. So you are essentially grabbing the product and factorizing out the H members. And that can be written in this form. Yeah, this is also
That's
very fine, right?
that's just the definition of a quotient group.
Yeah, yeah. Okay, so the function fk equals hk is an homomorphism from H onto HK by H, and its kernel is the intersection. Wow, wait a moment. Okay, so we have a function f that is defined as the right coset of H, and we are saying it is an homomorphism from K onto HK by H.
Well, this follows from 4, right?
Yeah, but what about the kernel thing at the end there? How do you know the kernel is going to be the intersection?
Hmm. Well, this is a quotient group where you're trying to factor out H, right? H is the denominator, right?
Yes.
That means whatever elements that um, were originally in K that are being mapped to the identity by the homomorphism
Yes.
can only possibly be in that intersection, I guess.
Hmm. I think it's like the elements that were fully from H, they are getting factorized out. The elements from the intersection, they must be going to identity, and the remaining is everything that is on K, that is exclusive to K, I guess. Does that make sense?
Uh, yeah, I think so.
And then 6, by the fundamental homomorphism theorem, K by the intersection is isomorphic to HK by H. And this is referred to as the first isomorphism theorem. Um, this is talking about isomorphism between two quotient groups. That's crazy. Okay, so these are just the exclusive K elements, right?
Uh, well, kinda.
No.
Basically,
Actually, sorry. These are all the exclusive H and K elements, right? Because we are factoring out what they have in common. Yes, Maninho.
Yeah, basically, whatever is in common between the two will be mapped to identity, and whatever is left over is only in K.
And then we are saying that this is the same as... Wait, you said that this is going to be the things only in K, right?
Plus identity, yeah.
Plus identity. What happens to the elements that are exclusive to H in this situation?
They all collapse to identity. Alright, there. What happens to the elements that are exclusive to age?
Yeah.
Well, if they're only in age but not in K,
Yes.
they actually won't be part of the of the
Of this math here at all.
of the result. They won't be part of the result because you're dividing K, right?
Okay, so these are essentially all the exclusive elements from K, excluding the intersections with H, and these are all the elements from both of them, excluding the ones that are in H. So yeah, this makes sense that they will be met one to one, right? It makes sense. Okay, G. Does anybody have comments about G? I think this one, I think actually G1 is, I remember being easy. Let's see. If H is a subgroup of G, let S designate the set of all the left cosets of H in G. For each element A in G, define Ho A x to x as follows. Prove that each Ho A is a permutation of x. Well, easy, right? Because x is the set of all the left cosets, and this is a left coset. Done. Yeah, I remember G1 being like, man, if only every single exercise was G1 in my life. Um, prove that H blah 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 permutation of X defined by HA equals Ho A is an homomorphism. I mean, H in this case being exactly Ho A, and we know, okay, so we just have to prove that this is an homomorphism to prove that H is one as well. And the way to prove that is to say that Ho A is factoring out in its own homomorphic image all the left cosets that have A inside. Right?
uh, well, if Ho A is a permutation, that means it is an isomorphism, and every isomorphism is a homomorphism. So
That's cheating, but okay, that's fair. Prove that this set, which is the set of all the conjugates, all the elements of H whose conjugates are all in H, is the kernel of H, of the other H, I guess. How is that the kernel?
uh, it belongs to age, such A in age such that the
The conjugate is also in H. So somehow we have to show that this goes to identity.
hmm,
Mm, mm, mm. Ideas. This one has a hashtag. We can see the answer.
set of all elements of H whose conjugates are all in H.
Okay, the comment on G3 is, note that the range of H is a group of functions. What is its identity element? Well, the reason that the range of H is a group of functions is because you can vary on A, right? And then you're going to create a different hole every time. You're going to be using a different hole. I don't know how that helps, but that's what's written in the book.
Well, the identity element would have to be the identity function, right? And the identity
Probably.
function in this case would multiply by the identity of G, I guess.
Yeah, but how do you put the conjugate into the party? That's kind of
Well,
that's kind of what I'm wondering.
it's because every conjugate of the identity is identity.
No, yeah, sure, but how can we plug this into whole? Because that's what I think we're gonna have to do eventually. Because we have to prove, my understanding is, we have to prove that um, H is whole, and we are
Mm,
using elements that go from here to like feed H. And we have to prove that if you grab those elements and you feed them to H, all of them go into identity.
that's not quite it, actually. H constructs an instance of whole based on its parameter.
Yeah, that's what I said with different words. So if you change A to a B, you're gonna have a whole B, right? And if you have a C, whole C, and so on and so forth.
Hmm.
But I guess you said in a more precise way. That's fine. H is going to instantiate a different whole. That's okay. So if you grab an element with these properties, how can we show that this will go to the identity when applied to H? That's what I think we need to prove.
Uh,
Well, we know that this H is the same as this H. And we know for whatever thing we throw in there, the conjugate will also be in H. That's what we know.
hmm. All the elements of H whose conjugates are all in H. So it would be a normal subgroup of H, right?
Yes, yes. Well, I think this is a normal subgroup of G as well. This thing.
Well, we know for sure that the identity element will be in there.
Uh-huh. Yes, that is
Uh,
true.
and
My
I
intuition is
guess.
telling me that you will be, like there is something about, okay, in H you know that this will be there. So in one of the multiplications when creating the coset will be AX X A X inverse, right?
Uh, yeah, I guess this means that the identity, and actually more generally, every element that commutes with all elements of G will be in there, right?
Wait, repeat that.
Not just the identity, but every element that commutes with every other element in G.
Oh, so this is the center of G.
It's the intersection of the center of G with age, yeah.
Okay, how do you know by this description that it's going to commute with every other element?
Well, it's because that's the definition of the center, right?
No, no, kind of. Let's backtrack a little bit. Um, let's actually backtrack a little bit. So the definition of the center is what you said, but how does that imply normal stuff? I think that's kind of my question.
Well, every center is abelian, and every subgroup of an abelian group is normal.
Well, saying it like that is kind of like... Okay, I don't know if I got it. I understood what you said, and maybe we did some exercises in the previous chapters proving those facts. Yeah, I cannot find the center stuff. Okay, anyway. So what you're saying is that this is an intersection. Well, this is going to be an intersection of the center of G with H. Is that what you're saying?
And that would be the kernel of age, right? Which is all of the elements that age sends
Identity.
to identity, yeah.
I don't know if I got it, but well, let's move on. We have 14 minutes and there's more exercises to go. So now, yeah, complex numbers. Are you happy, Marinho?
uh, I'm not a fan of sine and cosine, but yeah, I do like complex numbers.
No, I'm a huge fan of sine and cosine. When I did the engineering, these things are very handy because they are very, very powerful and they can do many things. The unit circle in the complex plane consists of all the complex numbers whose distance from the origin is 1, right? And I didn't know this, but apparently there is a contraption that represents cosine and sine in addition, which is cis. I never heard of that in any book back in the day.
Hmm.
And then we have to prove that the cis thing is actually, well,
Yeah,
there's a
there's a
typo
typo
here.
there.
Yeah, but this is gonna be part of the thing to go to the homomorphism operation, because this is one of the properties, right? We've seen this before. And then after we do that, yeah, we're gonna use this to prove that to prove that cis is a group. Then if you say that f of x is cis of s, then we're gonna go to homomorphism. Then we say that the kernel is 2 pi, which, well, if you know sine and cosine, that's gonna make sense. And then we finally go using the theorem to talk about the isomorphism. And then we say that if you have a G, cis 2 pi x is an homomorphism from that to T, whose kernel is integers. And then we talk about another isomorphism. Yeah, I think this is pretty fine. Like intuitively, I don't have to do the mechanical parts to understand. Like this is a very constructive. I shouldn't use that word, but like very pro. The progression from 1 to 7 is very natural to go to the conclusion. Second isomorphism theorem. Oh, before we continue, so does anybody want to talk about H more? More about H?
You held yourself back from saying constructive because of constructive logic, didn't you?
Well, it's because it's a technical term. If I say that I'm constructing a house, somebody can be pedantic and say, actually, you're building a house. Because that's a technical term and blah, 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 blah. So instead of going there, I'm just going to say, okay, this is just a natural progression of the idea.
Yeah, I don't have any other comments.
I. Let H and K be normal subgroups of a group G. And there's a typo here because this K should be capital. with h containing k, define phi as g by h going to g by k by this coset, this function that interacts with cosets. Phi is a well-defined function. We have to prove that, right? So it's for the same input, it always goes to the same output, I guess. That is, if HA equals HP, then phi HA equals to phi HB, which is going to be true, right? Because that's going to go to KA and KB, which are different. So,
Unless A and B are equal.
yeah. Then phi is an homomorphism. Um, well, we have to do the checks, right, with the criteria that the book established before. So phi is surjective, which means that we are going to individual elements of the image.
Surjective actually means the image covers every possible element in the
Yeah,
set.
sorry, that's injective. My bad. I said injective, not surjective. We are covering the entirety of the image. And then the kernel of phi
Is K over H, apparently.
is k over h. So how about that? So does anybody have any clues on that one? Just before we continue, we have more stuff to talk about, right? Yeah. Yeah, actually let's speed this up. We have 9 minutes to talk about the rest. So the kernel of phi being k by h. So we are essentially talking about the elements that are exclusive to the kernel. Well, that makes sense, right? Because here's the thing. If you are in H, this is going to map you to someone else, which is not identity. If you go only with an element of that is in K, because remember, H is in K, which means that H is like inside of K. So there are elements of K that are not in H. And the output of this would map everybody to identity because they are only in K. So to me this makes sense. Because if you are in H, you're going to be mapped to someone else. Conclude that
I think there's a typo with the parentheses there, probably.
yeah, there is 100% a typo there in the parentheses. Okay,
Yeah,
so
because this looks like the rule for what happens when you have a fraction as the denominator of another fraction, like how you reduce that, right? You have to.
that's kind of funny
Uh,
actually. Yes, it is definitely how fractions divide, yes. So we are missing a parenthesis and a slash here.
yeah, that makes sense because, like algebraically, you turn that into a multiplication, but you flip the denominator, right? So it becomes g over h times
H divided by
h
K.
over k,
Yeah.
and that, yeah.
Yeah, but that's kind of funny. Like, what does that mean in this context? We have two quotient groups, and you are um, trying to understand what is the quotient group of that. And the quotient group of that cancels out one of the subgroups, one of the normal subgroups. Okay, but this is the catch. We know that one subgroup is inside of the other. Well,
Yeah.
I guess the intuition is that you have an outer group, like a group, then you have two subgroups, but one is inside of the other. You can completely eliminate the smaller one. Damn. Okay. Okay.
Yeah, this is kind of interesting.
Okay, that's cool. Okay, now the correspondence theorem. We have an homomorphism, If S is any subgroup of H, let S star be all the elements of X in G, in which when you apply X to F, you're going to go to one of the permutations. We have to prove that S star is a subgroup of G. Well, this is just you just need to apply this to the rules of subgrouping, right? So
Kinda, but not quite. This is about if you know that something is a subgroup in the output, you need to be able to find a corresponding subgroup in the input, basically.
in the output.
Yeah, see, S is a subgroup of H, and you're trying to find an S star, which is a subgroup of G. You see?
Ah. Okay, so you know that S is a subgroup of H. You can go to H via F out of from G, and you have an S star that is essentially all the possible outputs of F.
It's the elements of G that F takes to S in particular.
Takes to S.
Which is the
Yes,
subgroup.
yes, yes,
Yeah.
yes, yes, yes. Yeah, but that's the thing. I don't think we need. Wait, the first sentence that you said. Could you repeat that?
Okay,
The
S star is all the elements in G that if you apply F to it, it gives you an element of S, which is a subgroup of H.
yes. No, but you said something before that. You said something like this is about proving the subgroup of the input with the subgroup of the output, something like that.
Well, yes, S is a subgroup of the output, which is H. And then S star is the set that we're investigating, which is all the elements from G that F maps to an element of S. And then you have to prove that S star is actually a subgroup of G. Then you have to prove that the kernel is contained in that subgroup, and so on. You see?
Well, but that here's the thing. If F is a normomorphism, then we know that H is a subgroup of G, right?
Not necessarily.
I think that was in the definition of homomorphism. Let me check the book. Pretty sure.
It is isomorphic to a subgroup of G, but it H itself is not a subgroup of G.
Well, but that's my confusion. You can talk about homomorphisms even though the groups in question they have no relationship to each other. I don't think that. Well, my intuition is that doesn't make sense. That's what I'm looking
There is
for.
a relationship. They all use the same operation. Alright, technically the F needs to map the operation as well, so there must
No, no,
be.
no. But you guys are right. In the definition of homomorphism, you don't have G and H. They don't have to have an explicit relationship aside from the operation being preserved. So it's not necessarily a subgroup. I see. Okay.
But for the exercise, you can use the fact that the operation is preserved to go from S back to S star and prove that that is a subgroup because S is a subgroup.
Pretty crazy. Well, we have two more exercises and we are kind of out of time. So K is pretty crazy, right? So this is like prerequisites. Remember this thing and this thing. And probably number theory because there's primes and divisors in here. If
Yeah,
G is a group and P is any prime divisor of what is this?
the order of G.
The order, yes. It will be shown here that G has at least one element of order P. We've seen this before, I think. This has been already shown in abelian groups. Assume that G is on abelian. The argument will proceed by induction. Let the order of G be equals to K, and assume our claim is true for any group of order less than K. Let C be the center of G. Let CA be the centralizer of A for each A in G. And let K be described by this sum, by the class equation of G. Yeah, I don't know what's going on with this exercise. Gotta be honest. Comments about it.
Well, it's more number theory, basically.
And subgroups of P groups. Let P be a prime number, of course. Let P group is any group whose order is a power of P. It will show here that the order of G is equal to P to the power of K. Then G has a normal subgroup of order Pm for every m between 1 and k. The proof is by induction, and therefore assume our result is true. What is going on with that? For all something smaller than G. Proof parts 1 and 2. Yeah, and then it goes, okay, so if you are not dumb, just go further. I'm dumb, so I didn't go further actually.
I took a look at those. Yeah, they go pretty deep.
Yeah, okay. So let's summarize these K and L exercises. So what are we supposed to conclude? What is Cauchy's theorem? Let's ask that question. Does anybody know?
Well, if the order of G has prime divisor P, it will have at least one element of that order, and that will be true for, I guess, for every prime divisor of the order.
Wait. So you were telling me that if the order of a group is P,
Not
no,
necessarily P, any multiple of P.
any multiple of P, like any factor of P, I should say, right? Because there's maybe there are more prime factors in the order there, right?
Yeah, basically for each prime factor, of the order of the group, there will be at least one element with that order.
That's crazy, man. Like, how can you say so? That sounds so fucking strong, but number theory, I guess. And what about L, subgroups of P groups? Wow, this is actually talking about the order of the subgroups, of the normal subgroups. So if the order of the outer group G is pk, p to the power of k, then G has a normal subgroup of order Pm for every m between 1 and k. This is insanely strong to say, right?
Well, number theory.
Sure. Okay, so next time we're going to be talking about rings, right? So I hope it's not that crazy. I didn't take a sneak peek of it on it, but anyway.
It's one ring to rule them all, and in the darkness bind them.
Okay, I'm gonna stop the recording now.